I'm going to move to the test-driven design. So basically, what's happened? We have 5 types of primary controllers, and then we wanted to compare them. We want to compare in a fair fashion. We have actually there is different operating conditions. It can be connected to the grid, and then we also have the transitions actually, and then also it can operate in island mode. And when in island mode, there is I would say operation with linear load, with no linear load, with a short circuit. So if you add up this combination, we end up with hundreds or even thousands of simulations. So in order to, so we wanted something that can be done automatically and then generate reports. So basically, I'm going to follow the presentation over here. Let's see if I can get organized in my screens over here. Okay, let's move ahead. Okay, in order to evaluate and compare the performance of the different primary controllers derivative, let us define a case study. Okay, the microgrid that we use to compare these controllers are comprised of 2 identical distributed energy resources feeding linear load, no linear loads, and then we consider both the grid connected and the island mode, as well as the transitions. Among the transitions, we just consider one transition, that is the unplanned island. So this is unplanned island happens when there is, for instance, a fault at the grid side, and then we have to disconnect the microgrid from the main grid. So we understand that this is the most critical transition, since another transition the microgrid central controller is able to define the set points of the DRs and bring for instance, the active power to the grid to 0 and then open the switch. So this is kind of doesn't give you any surprise, I would say. So this is the reason that we focus in the unplanned island in terms of transition. So note that we have multiple scenarios to evaluate and compare. Therefore, an automated tool for testing and report generation is desirable. The Typhoon test integrated development environment is an alternative to create test scenarios, capture signals, apply transformation in a Python environment. Initially, the test is parameterizing by defining, for instance, the microgrid rated voltage and frequency, the DR rated power, as well as characterizing the events to be captured in the different operating modes, as well as thresholds like voltage and power and so on. So basically, it's possible to define these quantities in this in a Python script. Okay. So once the test is finished, the results can be displayed using a test report tool. In this case, Aluri. This slide illustrates the results for operation in island mode, where the details of the operation for linear, nonlinear, and short circuit are easily inspected. So we are both in the steady state and transient. So basically, this helps our life. Let's start with looking at grid-connected dispatch steady state test. This test evaluates whether or not the active and reactive power exchange by the DR with the grid is within the envelope that we have defined as 15%. So this test have been evaluated for the 5 primary controllers that we have considered. So we have this donut chart showing the results. So we see that the two integrator droop and then the virtual synchronous generator with the reactive power computed at the POC have passed in all results. The droop itself is the one that somehow we have already predicted these results on the steady state analysis, small signal steady state analysis, that we had this problem with the droop. Okay, and then the dispatchable virtual oscillator got a good result also, and then yeah, in between is the virtual synchronous machine with the reactive power computed at the gap. So in order, so you can parameterize the test, define the frequencies where this the steady state characteristic will, the grid frequency where the steady state characteristic will be computed. You can define this thresholds, the 15% threshold. If you want to reduce, you can reduce it. You can define the voltage that you are going to test it, and so on. Okay. So the first result here shows the droop, for the droop control. All this considered primary controller have a very good response in terms of frequency watt characteristic. So the results are very good. As here, similar what we get there in the small signal analysis, this test-driven design revealed that the droop control suffers in terms of following the desired steady state droop characteristic. And with the true integrator, the droop solved this issue. So both for the frequency and the voltage droop characteristics are very, very good. The DVOC in terms of frequency has a good result as well. So it just failed in one voltage close to the lower limit where it does not dispatch the full or the required reactive power. Let's move on. So this is, as usual, the frequency droop characteristic is okay. However, the voltage droop characteristic for the virtual synchronous generator with the reactive power computed at the gap has an error. So this is attributed by the fact that you have a reactive power consumption, I would say, or reactive power associated with this virtual reactor. So this is not taken into account. The reactive power that is measured is at the POC. So since this reactive power that is regulated is at the computed using the electromotive force. So there is this difference associated with reactive power associated with the virtual inductor. Okay, with if you move the point where you measure the reactive power, this drawback is solved. As a summary for this steady state grid connected dispatch test, we can say that our primary controller passed the frequency support test. The droop present a significant error on the voltage VAR curve among all other primary controllers. The virtual synchronous machines with reactive power computed at the gap failed in the voltage VAR curve, which is attributed to the fact that we have a voltage drop across the virtual inductor. Even though the DVOC failed in a point of voltage VAR curve, its performance was good, considering that we probably are going to have a secondary controller that will compensate for this difference on reactive power. So in order to compute the, so this is just a detail, when computing the voltage VAR curve, we use the voltage at the POC of the DR, not the voltage at the grid. So we move to the second test. This is the transition mode test that evaluated the steady state and transient behavior of power sharing frequency when unintentionally disconnecting from the grid. This donut charts, they summarize the results. So we have we disconnected with the set points of reference power at different levels. And also we consider that this connection have different condition for the load in the microgrid. You can disconnect it with full load at the microgrid, but you can connect it with no load at the microgrid. So the behavior, the transient behavior will change depending on these combinations. So here the DVOC have the best result, I would say. So, and then the droop control also, droop control is a little bit, okay, let's move. I don't remember exactly what's happened in the droop control, but let's see what's happened. So you can parameterize the test over here. You can set the reference point for the, here we have 1, 2, 3, 4 tests. The first test, we have active power and reactive power set to 0. And then we intentionally disconnect the microgrid from the grid. Unintentionally using no load, with no load, okay? And then you can have this different combination. The last test, we have the reference set point for active power equals 0.7, the reactive power also 0.7, and then we have full load. So we can set the threshold of acceptable voltage, here the RMS voltages. We can set the settling time, acceptable settling times with 1 second, acceptable frequency settling time, acceptable error in steady state error, that 20 volts here, and acceptable steady state error for the frequency as well. Okay, so once you do that for the droop control, what's happened here, it's saying that the test revealed that it fails in the test number 3. So in the test number 3, there is an overshoot that, there is an overshoot that's exceeded the, no, it passed on that one. So it fails on the steady state error. So the maximum steady state error, 20 volts, is in 29 volts for both DRs. And it passed, it just failed in the steady state error, say, okay, so your steady state error is larger than it's supposed to be. Okay, again, the second test, this transition to an intentionally island with the set point in 0.7 pu with full load, it fails as well in the steady state error that is beyond the 20 volt threshold defined. Power sharing. So how do we do power sharing measurement? Actually, we take us, the two DR are the same power. So we set one DR as a reference and define a envelope around the power delivered by one DR. If the power delivered by the second DR is within this envelope, so we say that it passed. But if it's out of this, so there is a power mismatch. Okay, the power sharing is not proper among the DRs. Okay. Okay, let's move on this one. So it fails because, it is during the transient here, when there is the disconnection, okay, with no load, I would say, what's happened is that during the transient, it's out of the envelope defined. But no, we have to analyze carefully these results because you see, this is not that relevant. So in steady state is within the desired envelope. So let's move to this test over here that is related with the virtual synchronous generator with the reactive power computed at the gap. It fails because the frequency, steady state error of the frequency is below the 3 hertz limit is 3.12 hertz. So it's almost to get there, you know. So yeah, you have to, maybe if you change the parameters a little bit, you can get the right result. Let's move on. So the second test also changed because this is a full load now. It's the previous one was a no load. Here it's a full load. So we have the error of steady state error greater than the predefined threshold. Okay, so now it's the case of the virtual synchronous generator with the power computer at the POC. So it fails in 3 tests. In this case here, it fails because the settling time, it exceeds the defined settling time. So you have this slow mode over here that make the settling time for the frequency larger than the threshold. That is 1 second. The second test failed because of active power tracking. Yeah, but I wouldn't say that is that bad in this case. Okay. In the third one was the frequency also. That is a little bit out of the range. It's 3 hertz is what the threshold here is 3.2. So yeah, it got bad grades, I would say. But if you review it a little bit carefully, maybe you can retune the parameter and make it get better results. In summary, what we have from this test, the automated test point out that the VOC represent the best results. Detailed analysis for this test, actually. The detailed analysis revealed that the 2 integrated droop and the virtual synchronous generator with adjustment in the control parameter could also result in good results. The communication delay, also it's important in this case, communication delay between the microgrid's control system and the DR could change the results. So this is one important issue to be pointed out, because there is this transportation delay between the center controller and the DRs. So this is when the unintentional island happens. What's during a couple of hundreds milliseconds or tens of milliseconds, the DRs will be being island mode, but they think they would be in grid connect mode. So this is might change the result a little bit. How we are with the time?
We have yet maybe 10 minutes.
10 minutes. Oh, okay, so it's fine. So we are almost finishing over here. Okay. So in island mode, we consider 3 cases. We have linear load, no linear load, and short circuit. Okay, in this case, the droop control performed better. Okay, so we have the performance is, the worst performance was with the synchronous generator with the power computer that at the POC. Okay, so you can parameterize as we had before. So I'm going to move to this to the important point. That is the short circuit. So the short circuit is it was the toughest test to be passed. So what's happened is that power sharing was the cause of the failure on the during the short circuit and after the clearing the short circuit. So in some cases we notice, as in this example, that the DRs were not able to restore the voltage and frequency to their nominal value, and they start to exchange active and reactive power among them. So this is the case of 2 integrated droop control. So probably the DR will trip, and then everything have to start from 0 again. So this is, yeah, the DVOC, as Professor Marcio mentioned before, it eventually recovered the voltage and frequency to their nominal value. However, the time that he required the time interval required to recover depends of the duration of the short circuit. As the longer the short circuit, the more time it takes to recover from this short circuit, as shown over here. This is for a 50 millisecond short circuit. This is for a 200 millisecond short circuit. So we see that the DVOC took a little bit longer, but it recovered to the nominal frequency and eventually, right? So the problem is that the power quality issues associated with this interval that is not in steady state. Okay, so we are just showing here that we have implemented the current controller to limit the current. So during the short circuit, the current are the limit. and then in order to protect the semiconductor devices. And then let's move on. So this is this is the behavior of these virtual synchronous oscillators. Also took some time here. After short circuit, there was a time constant in that where the voltage was larger than it's supposed to be, and there is this peak of voltage just after the short circuit is cleared. The voltage jumped, to very high values. So this is also it's a concern in terms of power quality. Okay, I'm going to move on. The results follow similar pattern. The short circuit, I think, this is in island mode. This is the biggest challenge that we have faced over here. In summary, the test-driven design provide a holistic, I would say. You can see the overall picture to evaluate the performance of the primary controllers, pointing out the strong and weak points of each alternative. So the droop controller is the simplest one. Also there is a very strong point for the droop control in the terms of short circuit, because it behaves properly during the short circuit and when recovering for the short circuit. So, but it has this large dispatch error when connected from the grid. The two integrator reduce this error at the price of penalizing the behavior of short circuit. So there is a trade-off that you have to consider here. So the DVOC demonstrated to be a strong candidate for primary controller as well, just requiring attention for the short circuit case after clearing the short. And the strong point associated with the virtual synchronous generator is the fact that you can adjust the steady state and the transient in terms of inertia, I would say, independently. Okay, so this is, but you also have to address the issue associated with the transient after recovering from a short circuit. Finally, I would like to say that all the material that we have seen with the Python script and the report generation will be available soon in the Rio Academy site under the module number 5, because we have already 4 modules over there. We have one module that address the PLL, another module that address, I would say, current control, and then PWM, and another one that addresses outer loops. And then module 5 will address this primary control that is similar to what we have seen over here. All the files are going to be available over there.